We have a sample problem here. So the graph, which we can see, this graph represents a mass spring system oscillating in simple harmonic motion. The displacement or position of the mass is shown over a time frame of 10 seconds. The displacement is negative 7.07 centimeters at time equals 0, at time equals 4, and time equals 8 seconds. So A, write the equation for the displacement or position of this simple harmonic oscillator as a function of time. So we're wanting to find the equation of motion, x of t. And we want to write it in such a way that all we have to do is plug in a time and we will know the position of this mass. So the generic equation we have is the position of an oscillator is equal to A cosine omega t plus phi naught. A, amplitude, is the maximum displacement, the maximum distance the mass oscillates from equilibrium. When I come over to my graph, my vertical axis is the displacement. X equals 0 is equilibrium. We can see that this graph oscillates between a positive 10 and a negative 10. So the amplitude is 10. The units I get off of this label of the axis. So it's 10 centimeters is the amplitude. The other piece of information I can read off the graph is the period. The problem is telling us not only is the initial position, so x naught is negative 7.07 centimeters, but it has that same value at time equals 4 seconds and at time equals 8 seconds. So this system is oscillating such that it's passing through this same point every 4 seconds. That's what we define period as. It's the amount of time, so the 4 seconds is required for this mass to oscillate all the way to the right. So if this mass was on, in my picture over here, this would be the negative 10 centimeters. This would be the positive 10 centimeters. So initially it's moving to the right and it's headed towards this maximum positive displacement. But to finish an oscillation, it needs to go all the way back and come and get to this same point where it is moving to the right again. And so an oscillation means it starts here, goes all the way to the right, all the way back, and then back such that it's at that same location again. So according to our graph, that takes 4 seconds. As far as our equation goes, that period will be used to calculate our omega. So omega is 2 pi f, but f is 1 over period, so omega is 2 pi over t. So in this particular case, we can say omega is 2 pi over 4. This gives us our units of radians per second, which is our SI units for omega. So we can say that omega is pi over 2. So that's not the phase shift, that's how fast this mass is oscillating with time. So as of right now, we can say that the position of this oscillator is 10 centimeters times the cosine of pi halves t, but we have not yet accounted for this phi naught. And again, the phi naught is the shift. A regular cosine, just cosine function in and of itself, starts at a maximum positive value. So this particular graph is not starting at a positive maximum value. So we need a phi naught value to represent how that function is shifted and thus account for this initial position. All right, to do this, we need to put in the value of the position at time equals 0. Now this, well, I'll write it out. Pi halves times 0, because we're saying at time equals 0. So this is 0. So we have negative 7.07 centimeters. We probably shouldn't skip steps yet. So right now, I have negative 7.07 centimeters is equal to 10 centimeters cosine phi naught. So I need to divide both sides by the 10 centimeters. So I'll have negative 0.707. The units are going to cancel, and that will equal cosine of phi naught. Now remember, we want phi naught to be in radians because omega is in units of radians per second. That means the omega t term will have units of radians, and in order to add the quantities, they have to have the same units. So I'm going to put my calculator in radian mode. And take the inverse cosine of the negative 0.707. All right, let me plug that in. So inverse cosine I'm getting 2.356, which we don't have that many sig figs. We have 3, so I'm getting 2.36 radians for my phi naught. So we have to decide when we plug this back into our equation whether we have plus or minus this value. To figure out whether or not we need to put plus or minus phi naught into our equation, we need to come back to that relationship where we relate the motion of the oscillator to a peg on a disc. So again, our disc would be rotating counterclockwise. The center of the disc represents the equilibrium position, so the peg would have to be along this line. Because again, we're talking about as if we were shining light on the peg and seeing a shadow from where the peg was located. So the peg is either up here, option 1, which means it would be rotating this way, counterclockwise, or the peg is down here in order to get a shadow that matches up with where the mass is at time equals 0. So if the peg's on top, it's rotating towards the left. If it's on the bottom, it's rotating towards the right. Which translates to, if we think about the shadow up here, the shadow of this top peg, the shadow would move to the left. The shadow of this bottom peg would move to the right. So this is the correct situation for this particular problem. the angle we have calculated is the angle between the positive x-axis and whichever peg is the correct one for the situation, for this particular problem. So since this peg is down this way, we actually want the value that's negative 2.36 radians, because if we go down clockwise from the positive x-axis, that is a negative angle. So the equation of motion, we can write the position of this particular oscillator as a function of time would be written as 10 centimeters cosine of pi halves time minus 2.36 radians. This is the answer to this part A up here, where we were asked to write the equation for the displacement or position of the simple harmonic oscillator as a function of time. This is our answer to part A. We could plug in any time we want, plug it in our calculator, and that would give us where the oscillator was at that moment in time. So when we're asked about writing the equation that describes the motion, that's what we mean here. Now, B asks us to find the velocity of the mass at t equals 3.33 seconds. So not the position. This equation is the position or displacement. It's where the mass is at any moment in time. To answer part B, we need to get the velocity equation. And we do that by taking the derivative of this function that describes the position. We take the derivative with respect to time. So time is our variable. All right. Now, total random side note. We don't use primes in physics or engineering to represent derivatives. We use dots above the letter, and so actually not v dot, it would be a dot above the x. So not x prime, which you learn the primes in your math classes, which is fine. We just don't typically use that in physics or engineering. We use these dots. Primes are often used to represent just another value of x. So that's just a side note. All right, so let's take the derivative of our function down here. So our velocity as a function of time, we have our 10 centimeters still. Derivative of cosine is negative sine of all the same stuff. And then we have to take the derivative of what's inside the parentheses for the cosine. So when we take the derivative of that, we're going to get pi halves. Velocity function, let's see, we still have our negative sign. 10 times pi over 2 is going to be 5 pi. The units here will be centimeters per second, because we have centimeters on the amplitude, the 10, and then omegas in radians per second. That's where the centimeters per second comes from. And then we have our function, sine of pi halves t minus 2.36. So this equation describes the velocity of this mass at any point in time. We can plug in any t we want, and that will allow us to calculate for the velocity at that time. So we're putting in a time of 3.33 seconds from the problem. That's what it's asking us about. Now, here, this term in here is in radians. So make sure when you're doing this calculation that your calculator is in radian mode. So let's see, negative 5 pi times the sine of of pi times 2 minus 2.6. I'm getting negative 4.20. The units, again, will be this centimeters per second, as mentioned before. This is the velocity at that specific moment in time. The negative sign means the mass is moving in the negative direction. So if it is moving on a horizontal surface like this, it's moving to the left. And it's moving at a speed of 4.2 centimeters per second at that moment. That's what that means.